Hey, Lesedi, how are you?
Tempo, wow, it's so
Yeah,
nice
man.
to see you. How's UJ?
UJ is good, man. I'm in third year now, going strong. And you, are you teaching?
Yes, I'm at CC Primary, grade 1s.
And?
Sure, I tell you, hey, it's tough. But Tempo, it's so rewarding at the same time. The children are like little sponges. Their mind just soak up everything.
I'm learning all about children's minds now.
Oh yeah, you're in your third year now, so you're probably doing the course on childhood cognitive development.
Yeah, there's this section on children's mathematical cognition that's quite tough.
Okay, yes, you know what? I used to also think so when I was studying it. But once you're in the classroom, you can see mathematical conceptual development in all children. You know, you see it in very young children as well. That's when it really changed my understanding.
How do you mean?
Think, for instance, wait, do you know that young children start life with an innate knowledge?
Oh, you mean their innate number system?
Well, Tempo, I'm impressed, hey?
Yeah, man. There's just this tutor who really drills us. I mean, he's a real teacher preacher.
Excuse me?
I'm sorry.
Well, has he taught you that young children actually have a number sense of up to the number 3?
Yeah, that's exactly what we discussed the other day in my tutorial.
So we all start life with the foundational ability to estimate the numbers of objects in a set. And we're born with the ability to compare such approximate numbers and combine them with simple operations such as addition, subtraction, and comparison. Now, the human brain in some species have number sense, which is a seemingly analog sense. So that's analog sense of size of connection.
Wait, what's analog again?
Analog just means it's like what it is in your head compared to what it is in reality. So you have an idea in your head and you can represent that idea by something that exists in real life. So one represents the other, like an analogy.
Analogy. Hey,
If you look at one lot of chips in a packet, it's more than in another packet. It's an analog in your brain. You are born with it. Even someone like you can get this. It's part of our evolution as human beings. It allows us to quantify all sorts of sets. Food, friends, foes, and so on. Even some animals have this.
I have read that lions have innate or inborn ability to sense whether the other pride has fewer or more pride than their own. And they use this to work out if they could attack or not. In young children and other animals, this approximate estimated number sense seems to be the same, but it goes further than that. The human brain and other species can distinguish between 1, 2, and 3 objects.
I wish they could distinguish between your own chips and someone else's chips.
Well, KG, you're not supposed to be eating here anyway. And Zuki's absolutely correct. In experiments, scientists have established that babies and other species can distinguish between a right answer and a wrong answer when they're presented with a scenario involving arithmetic of small whole numbers like 1, 2, and 3. So, babies are born with this innate number sense, which is accurate between 1 to 3. But what's interesting is that babies show this innate knowledge of arithmetic, basic arithmetic facts like 1 plus 1 is equals to 2, or 1 plus 2 is equals to 3, or 1 minus 1 is 0.
No, man. Babies can't tell. How can scientists say they can? Did they ask them this?
Well, Tsepo, if you had done your readings for this tutorial, you would know that scientists have shown babies objects by adding and taking them away without showing them the final answer. And then what they do is they measure the surprise response of the babies when they do show them the final answer.
In the things we had to read for today, it says technology is now so good that it can detect this surprise response by checking an eye dilation, facial expression, and the body reaction captured on a video, or by sucking a reflex on a pacifier attached by a transponder to a computer. In this experiment, babies will show a greater surprise when are presented with wrong answers, such as 1 plus 2 is equal to 2, as opposed to a correct answer, 1 plus 2 is equal to 3.
Yes, and you would know that Karen Wayne from Yale University did this experiment back in 1992 at MIT. That is a smart university near Boston in USA, where people actually do their readings. When she showed babies a puppet theater where the baby was first shown an empty stage and then a screen was placed in front of the stage. Puppets were then introduced and taken away, and then the screen was lifted. If the wrong number of puppets were on the stage, the baby will react in a surprise response.
Wait, Jerry, why only up to 3? What about 4 or 5 or 6?
That's a good question, KG. Wow. Well, according to Dr. Keith Devlin, who's a mathematician from Stanford, and the math guy on USA National Radio, innate accuracy for addition and subtraction of whole numbers up to and including 3 does not extend to greater numbers. Now, scientists like him believe that this is because arithmetic ability beyond the number 3 seems to involve language, or at least the ability to assign symbolic names to objects, okay? And the ability to have a twofold symbolic meaning. So that would require training. In other words, teaching, and that is your job one day. Now, what's important to take note of is that children do have an approximate number sense for numbers that are bigger than 3, okay? And so do animals. But remember, this is just an approximation, an estimate, like Zuki was saying with the example of the lions. Now, this approximate number system, beyond the number 3, gives children an early intuition of number, which becomes essential for their later based school understanding.
I have a very interesting article here by McCarthy, Gilmore, and Spelker from 2007, whereby they gave 5 and 6-year-old problems to solve, such as Sarah has 21 sweets and she gets 30 more. John has 34 sweets. Who has more? These children have never received instruction with numbers of that size, nor with concept of addition or subtraction. Yet they performed 85% better than chance on this complex arithmetic test, regardless of their socio-economic status.
Wait, if kids can do maths anyway, why do you have to teach them in schools? And why am I here taking this difficult course? What is this?
No, you still have to teach them. And you're not here wasting your time. It just means they're performing based on approximation and their reliance on the approximate and estimate number system. Now, your ability to approximate just gives children, intuitions to solve problems that they've never experienced. The cognitive neuroscientist Dahan says that approximation just lays the foundation for subsequent construction of higher level arithmetic concepts. Now, for that, you would need very good instruction. For more complicated maths is cultural. It was designed by humans to understand their world and the different magnitudes. Maths is about magnitudes.
Wait. Here we go again with the big words. What is magnitude?
Oh, I can tell him what's magnitude. I asked Professor Henning the other day. She explained it to me like this. Do you know what is a magnifying glass?
Yeah.
It changes the way you see size. It changes sizes of something. Magnitude means the size of something. It can be long or short, big or small, slow or fast, loud or soft. Okay, I mean the size of the decibels. This is the magnitude of sound. How much of something is there? How much of noise? How much of light? How much of sound? How many square meters? It can be anything that you can think of, man.
This is not too difficult to understand. So, as you guys are speaking, it sounds as if kids already know everything about maths. It's all inborn, right?
Yes.
But then again, you say some stuff happens with instruction. So, are you saying that kids still need to learn mathematics, arithmetics?
Yeah.
This is so confusing.
Okay, look at it as if there's an innate part of us that can estimate what's bigger, smaller, longer, higher, etc., or more or less. It's like a guess. What's your language?
Zulu.
Okay, now how do you say, what's guess in Zulu?
Qagela.
Thank you, Maman. Ukuqakela. Now, this is what kids at that age do. They qakela. They can be able to tell the difference between 8 or 2 when you show them 8 or 2 sweets. And ukuqakela, number sense, that is what we build. Our building of arithmetic, etc.
I want to know, where does this happen? Where in the brain? I mean,
That is a good question. Through functional magnetic resonance imaging, fMRIs, which is a very smart way of scanning right into your body, like into your lungs or heart or your brain. It's much smarter than x-rays. They take scans of your brain and they can see where activity is in the brain in milliseconds. Now think of it, just the thousandths of the second. Swoosh! In these scans, the part of the brain that is activated lights up on the screen. Now through the fMRIs, an important area of the brain for number sense has now been identified. At the top back of both hemispheres in the brain, within the parietal lobe, in the cortical fissure, there's a section known as the intraparietal sulcus. This area of the brain is active whenever you think of a number, whether spoken or written, or as a word, or as an Arabic digit, or even when you merely inspect a set of objects and think about its cardinality. This area even acts when we talk about subliminal number, when you don't really know what number you saw, like next to the road, when you see a number that's written on a sign. Right? The intensity of the activation in this part of the brain is also related to the difficulty of the arithmetic task at hand. The more difficult the math problem you're working on, the more this part lights up.
So in a nutshell, like Diana says, a child's competence for the arithmetic in the future is grounded on their foundational representation of approximate number, which is inherited from our evolutionary past. Further on, this arithmetic development also relies to a large extent on the ability to connect this quantity representation with other representations of the linguistic or Hindu-Arabic symbols for number, as well as the recycling of the nearby cortical region involved in representing space.
Oh boy, Zuki, like, did she swallow the textbook or something? What is she saying?
What she's saying is that a child's ability to do math sums in the future is based on their ability to estimate or guess or uqakela numbers and sizes when they're young. And this ability has developed over the ages as human beings have developed. Now, the child must also link their guessed ideas about quantity to language, so how they express it or name it, and also to the numerical symbol, 1, 2, or 3, to also parts of the brain which deal with size, length, width, volume, etc.
You guys are killing me.
KG, you can do maths in the future because when you are young, you can guess amounts. Humans can do this because of evolution. When a child gets to school, a teacher needs to instruct a child how to link these guessed ideas of numbers and one-on-one correspondence, like this. 1, 2, 3, and 4. Then 1 represents 1, and 1 in word represents 1, meaning also the child learns the symbols.
Well, Tapo, I'm impressed. Look, here's my ride.
Oh yeah, I'm also getting on this one. Sanbonani.
Whoa, Tapo, from what you just told me, you remember quite a bit about children's innate mathematical knowledge.
Yeah, it's okay when I hear it in the lecture or tutorial. It all makes sense. But once I'm in the real world, I just cannot apply this knowledge.
Let me see if I can give you an example. Sawubona ma.
Yebo sawubona sisi.
Unjani mama?
Sikhona ninjani?
Ma, ubani igama lakho?
Yimi uLindi.
And the little one?
Ubuhle.
Ooh, buhle ngicela ubuhle ajike. Wow, Buhle, you're such a big girl. Hey? Are you clever also? Can you tell me? Elipitex in a enebantu abaningi. Which taxi has the most people in it? Very good, Buhle. That taxi has many people in it. Now, take a look again at these taxis and tell me which one has abantu abancane ngaphakathi. Good girl. So you see, Tepo, although she could not tell us the exact number, she could still tell us there are fewer or many people in which taxi. She thus based her answer on estimation.
Oh, I see. That is a really cool example. Thanks, Lesedi. But what I don't get now, sorry ma, I'm sure Buhle can count, right?
Yes, she can count very nice, 1 up to 10. Count them down from 1 up to 10.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
You see?
Wow.
Yes.
But if she can count, how come she could not tell us how many people were in that taxi?
She would probably be able to tell us if she had more time to carefully count each person in that taxi. But she will not be able to, at just one glance, tell us that there are 6 or 8 people in that taxi.
But what's the point of counting then?
But it is important to note that counting up and down does not necessarily give the child comprehension about the cardinality of number. Understand? Nani, can I?
Yes, you can.
Alright, can you tell me? And can you tell me how many sweeties there are?
1, 2, 3, 4, 5.
Very good, Buhle. There are 5 sweets. Manje, mango palena. Right? If I give you 1, can you count how many sweeties are left? 4. Very good, Buhle. Good, Buhle. Ngizokupha elinye. Now that I've given you 2 sweets, can you tell me how many are left?
1, 2, 3.
3. Now, Tepo, what did you see? What can you tell me?
Well, I noticed that she began counting from the beginning every time she counted. She could not just subtract the numbers and tell us how many were left.
Yes, even though she could count and knew that each object represented each number counted, she still could not add or subtract. In other words, Buhle has the ability to count out objects and small quantities. And that is what we call the one-to-one correspondence. So, only concrete perceivable objects can be counted by allocating precisely 1 object for each number. So therefore, the counting process always ends with the last number recited. In this case, it was 5, 4, and 3. So she cannot, however, take the numbers out of the context or the sequence, actually the rhythm of counting.
Oh, I see. So the names of the numbers 5, 4, and 3 only make sense as part of a longer sequence. They cannot be taken out of that sequence.
You've got it, Tepo. She has not yet learned that a number is an entity on its own out of the sequence.
The sequence is important though. Otherwise, why do I teach my child to count 1 up to 10?
Yes, the sequence is important to know, but it should not be confused that knowing arithmetic means that a child can count up and down. And that's the point that I'm trying to make.
So, the counting teaches the child the names of the numbers, their sequence and rhythm, and maybe later on arithmetic, which also has rhythm and pattern. Or am I taking it too far?
No, you are correct, because this natural rhythm in maths is also very important to take note of. The well-known maths professor Mike Askew also compared the pattern in maths, the pattern and rhythm in maths, not only to music, but also to the pattern in dance. He said, rhythmical aspects in music, or rhythmical aspects of music, and the patterning and sequencing in dance are also quite closely linked to the patterning in maths.
Hey, I noticed the other day when some of my steppy buddies were doing some move, there was such clear rhythm and pattern, which I can definitely identify in maths. Have a look at this.
That's the direct order. Do it now.
Yes, that is so cool. That is the pattern and sequence of maths. That should start with counting, but it should not stay there. With proper instruction, it should grow into something bigger. And that is what is important to note.
I got you.
Brings it to you like a preacher cause this lecture's heavy. So to all my future teacher, get your pencils ready. Cause the facts I be dropping, y'all already fleshy. It's mental food, hope your belly's empty. I'ma talk about what children do before they learn to count. Like when they view in two groups which has the most amount. Just after birth they use their number sense to figure out which group has the highest number in it with no doubt. Cause it's inborn, lives inside your mind like a unicorn. Lions, tigers and gorillas have it, man, it's uniform. Newborns learn how to count from 1, 2, 3 using analogical processes, y'all, it ain't a mystery. It's all internal. Estimations with approximation form foundation for future math inclination. Having this knowledge should not give you the revelation that a baby's number guessing brings math ability elevation in the brain. See, this is where it happens. The interparietal suckers goes nuts and get those numbers cracking. When you see him, read him or write him, it's an action. And that's why you even get addition or subtraction. Ever wondered why a child has to count out a set of objects before they say they total out loud? It's analog. Remember, already told you all. Just hope you internalize my little monologue.